welcome back to the STEM Village Virtual Symposium. Hope you enjoyed your quick break and, like me, you've got yourself a nice cuppa. I am Dr. Brindley Pearlstone and I'm going to be chairing the next couple of sessions, including this session of a couple of talks and the next one, which is going to have the track panel as well as some words from Sue Duker. So before we too deep into it, I want to just reinforce that we've got this survey. We'll be showing the link again after this session, and we'll be showing you the QR code to scan to get to that website throughout. So if you get a chance, please do fill in that survey. As well, we've got 2 talks in this session. So if you have any questions throughout either talk, please do use the Q&A function in order to ask them. And then after each talk, we will read out the questions if we've got time. And without further ado, it is time for me to introduce the first speaker for this second section. And that speaker is Hyun Youk. Hyun is going to give us a talk about baker's yeast. Now, through lockdown, I'm sure that all of us have turned our hand to a little bit of home economics, and I can't wait to see what it has for us. So if you are available, off you go.
Okay, so let me just share my screen here. Okay, I hope you can see the slide here. Yeah. Okay, so let's see. I'm going to play the slideshow. Okay. First of all, I want to thank the organizers for inviting me, but more importantly for organizing this symposium. I know that when I was starting out in science, I didn't know of symposiums like this, and at the time I was just coming out, and so I felt that being gay and doing science that I loved were sort of 2 distinct, unmixable sort of components of my life in a way that wasn't, I think, healthy. So I know that symposiums like this would have meant a lot to me back then. And I have to say, even today, as someone who runs a group, this really means a lot, and it's very important and very uplifting event for me even today. So I was incredibly honored when I was asked to present here. I've given talks at conferences before, but this one in particular is very meaningful to me. So I want to thank you for inviting me here. Since I am most qualified to talk about science, and in particular the science that I do, that my group actually does, that's what I will focus on today. So I am, my lab is currently at the Delft University of Technology in the Netherlands. But I'm also in the process of moving my lab to the University of Massachusetts Medical School in the United States, because as we all know, this is such a spectacular time to be moving there. Okay, so my lab is interested in understanding how living systems transition from being alive to being either really dead or just seemingly dead. We are also interested in the transition the other way around, in particular, how something that appears to be dead actually wakes up and re-enters a dynamic replicating state, which is definitively alive. And an example of something that appears to be dead, which we're going to talk about today, are the spores of the baker's yeast. So these are yeast cells that you use for baking and brewing beer. But when you starve those yeast cells, you can force them to form spores, which are dormant. And the question that you can ask here is, how can a still form of life, like a dormant spore, still have the ability to re-enter, wake up and re-enter a replicating dynamic state, which is definitively alive, whereas some other still form of life, which could be another spore that's nearby, unable to do so, and therefore would be considered dead. Okay, so that's what we're going to focus on today. But before talking about yeast spores, I want to demonstrate something to you, which is this idea that the question of what it means to be living or dead is a deceptively simple question. It's very easy to ask, but it's incredibly difficult to answer. And I would say that to date, we don't really have a rigorous quantitative definition of what it means to be living. But we do know of some hallmarks of what it means to be living. What I'm going to do is a couple of demonstrations. So first, I'm going to show you a movie that my group made with a microscope attached to a camera. And I'm not going to tell you what you're going to be seeing in the movie, but ask yourself during the movie whether what you're seeing is living or not living. Okay, so here's a movie taken with a microscope. Something is kind of happening. Okay, and now decide for yourself whether it's living or not living. And if you're like most of the audience I usually give this talk to, almost all of you would say that they are living, right? You would all raise your hand to say they're living. And indeed, these are the baker's yeast cells when they're happy, when they're in the presence of glucose and lots of nutrients, they replicate. That's a hallmark of life, self-replication. Now I'm going to show you a second movie, this one taken with my phone. Again, I'm not going to tell you what these are, but pay attention to these black spheroids that you see here and ask yourself again the same question, is it living or not living? Okay. So obviously my hand is shaking because my hand is not a microscope, but you know, watch the spheroids. And now ask yourself, oh, I'm going to stop the movie, whether it's living or not living. Oh, there we go. And if you are like, let's say, a group of scientists I usually give this talk to, then the response would usually be that about half of them are living, and the other half will say they're not living. Some of them might inevitably ask me, oh, what is it? And I would tell them it's a plant seed. But as I'm now going to tell you, that doesn't help you answer this question. I should also say I've also given this talk to a group of families with even 5-year-old kids during an open house at my university. And when I ask them this question, the response there is almost the same as the response I get when my audience is comprised of scientists. So I felt like, why am I like insulting the intelligence of 5-year-olds? So I crossed that out here. So now that you know these are plant seeds, how come that doesn't help you answer this question? Well, what would you do? You would give these plant seeds some nutrients, soil, water, and so on, and then see what happens. And if they germinate into like a plant, you would say, oh, okay, well, they were alive. If they don't, you might say that they're dead. But if you think about it, that's a very strange way of answering the question of, are they alive now, right? I'm not asking you what are they going to do in the future. I'm asking about now. And certainly if I ask you whether you think I am alive now, you don't need to know what will happen to me in the next 5 minutes. Okay, so, and in this case, I have to say that it's well known that some plant seeds do not germinate in the first spring, they wait for the second spring, okay? And if they never germinate, you can ask why not. So today, we're not gonna talk about plant seeds, but something that we work in my lab, which is basically like plant seeds, but spores of yeast. So when you starve yeast, baker's yeast cells, they form spores. They look like this. So this thing over here that I'm pointing to is what we call a spore bag, because inside of it, as you can see, are 3 individual spores. Okay. So now they look like this, and they appear to be dead in almost every discernible way until a key source of energy, namely the sugar glucose, appears in their environment. But until they do, they really appear to be dead. They don't move, they do not divide, they exist without any nutrients, meaning that you can keep them in water. The conventional view is that either every activity inside of the spores have either completely ceased, so metabolism or making of molecules like proteins have either completely ceased, or they're almost ceased. But it's been incredibly difficult to put firm numbers on these things. But the usual idea is that they're really not doing anything. That's something I'm going to come back to. And as I said, you can keep these things in water without sugars or nitrogen, any nutrients, and it's thought that they can exist for months to maybe even years. And so the question that we're going to address today to some extent is, if they appear to be dead, why aren't they? Okay. And in particular, if these are they appear to be dead, and if some of them are able to wake up, which we say germinate, the same language as in plant seeds, what actually determines their ability to wake up? Okay. And then, so that we're going to try to answer that to some extent today. And the second question we can ask and try to answer today to some extent is, how do spores age and eventually die? Now, I mentioned to you that it's conventionally thought that you can keep these spores in water at 30 degrees, let's say, and maybe they will live for, maybe you can keep them like that for months or years, after which, if you give enough sugar, you will wake them up. But that gives the sense that these spores are actually aging during some time. But that's very strange, because aging means that some process is occurring. There's a flow of time. If everything is still, there is no sense of flow in time. So how can the spores, if they're really still, or almost still, how can they actually age? What's actually happening inside of them? And we're going to try to answer that to some extent today. So all the work that I'm going to tell you about was done by really a remarkable PhD student in my lab, Theo Mayer, and it's been really a privilege for me to work with him. So since there are people from many different backgrounds and from different fields of science, I'm going to keep this very non-technical as much as possible. I'm going to skip a lot of details. I'm going to skip a lot of technical jargon, and I won't tell you everything, but hopefully all of you can at least get some of the main ideas here. So I'll just present some story with some main ideas, but not all the details. Okay, so we start with the question of, how do we even distinguish something that's dormant, so it's still alive, from something that's dead in terms of a spore? So here again is my spore bag containing 4 yeast spores. And the conventional way of answering this question, dormant or dead, is you give a lot of sugar, namely glucose. You give the maximum amount of glucose and then see what happens. If that causes the spore bag to open up, so if the spores start to germinate, you would say that these were dormant. If not, you would say that they were dead. But once again, we're facing the same problem, which is that I need to know what they will do in the future to know about their state of life now. And that told at least Theo and myself that there's something about dormancy that we don't really understand at a very deep level, and we wanted to understand that better. And to do that, we re-examined this conventional test by making some modifications to this protocol. First of all, instead of giving the maximum possible amount of glucose, we're going to actually give less than that. Okay, we're going to just change the amount of glucose we give them. And then with a microscope that's attached to a camera, we're going to observe what happens to these spore bags. You see 2 individual spore bags here. We're going to see if they wake up, when they wake up after getting the glucose, and how many of them wake up. So the movie would look like this. So you see here, this thing has germinated, and now this one has germinated. So from a time-lapse movie like this that you see here, and just by counting who wakes up when, we can actually get the data that you see here in blue. So what I'm plotting here is on the x-axis, the time after adding the maximum possible amount of glucose, which is 2%. You cannot go any higher than that. That's a saturating amount for yeast. And then what I'm plotting on the y-axis is what percentage of the population have germinated by some time. And basically what you see is that if you wait long enough after adding 2% glucose, everybody in the population has woken up. Okay? And there's nothing really surprising here. This is sort of the conventional test. Nobody is dead. Everyone woke up. But what was surprising for us is what happens if we now give less than the 2% glucose. So these smaller numbers are all smaller amounts of glucose. And the different colors represent the different amounts of glucose. And basically what you see is that if you give the less than the maximum amount, not everybody wakes up. So if you look at this yellow curve here, you see that only like 30% have germinated. And then the question is, what happened to the 70% other of the spores that are in the same population and are all genetically identical? Maybe they were kind of running a marathon trying to get to the finish line, but they kind of dropped it, right? Now, I have to say that all of these glucose concentrations are still a lot for a single spore. And we check that it's not that they ran out of actually glucose, because very little has depleted even at the end of time here. Okay, but now just to see what happened to the ones that didn't wake up, there's a way to test actually whether they're dead or not. There's a simple test. So what we do is we first give a relatively small amount of glucose, and we wait until no more germinations occur. So here we have a plateau. And then what we do is we add more glucose. So in this case, more glucose, so that the final amount is the final 2%, the maximum that you see here. And what you see is that indeed, the rest of the population actually do in the end germinate. So in the end, everybody has germinated. So the ones that don't wake up the first time are not dead. And long story short, for details that I don't have time to show you now, it turns out that the ones that don't wake up the first time are in fact getting ready to wake up if they see more sugar the next time. And that means that they are using the glucose they get the first time to start making things that they will need in order to replicate again. So these include things like components of a new cell that they have to build, and so on and so forth. And in fact, by doing so, these spores, which we say are now primed in dormancy, are able to wake up faster upon seeing more sugar next time than they would have had if we were to give all this glucose all at once. Okay? And I won't go into further detail here. But that still doesn't answer the question, which is what determines who wakes up the first time and who doesn't? And to answer this question, we had an idea, which was that the ones that don't germinate the first time have different internal states than the ones that do. Now, what are internal states? Well, these are various molecules that must be stored inside the spore, like ATPs, the molecules that carry energy, ribosomes, which are required to make proteins, the workhorses inside a cell, and so on and so forth. So we don't need to know exactly what comprises an internal state, but it could be all of these. And then what we thought was that, well, maybe a given amount of glucose, for a given amount of glucose, only some of these spores have the right internal states to wake up. Now, how are we going to test that? Well, we had a hypothesis. Suppose that is the case, and suppose we can deplete some of these internal resources before we give them sugar, okay? And then, intuition tells us then if we do that, and if we give them sugar, then less spores would be able to germinate. So that was the hypothesis. And how are we going to implement this? Well, we had this idea that let's suppose we can force the spores without any nutrients to start making something that's really useless, namely a green fluorescent protein called GFP. Its only job is to be green, okay? It does nothing for the cell. So that presumably takes up some resources that are stored inside the spores that should affect the internal state. And so if we give them glucose, we think less should be able to wake up, okay? And, but what was unknown at this point was that, remember the convention tells us that these spores are quiescent, right? They're dormant. They're not supposed to be able to make anything that you want them to make. That's why they're dormant. So can we even force them to express GFP? But we decided to try it anyway. And the way we do it is actually quite simple. The details here aren't important, but you basically build a gene circuit. So it's a circuit of interacting genes that regulate each other's production. We build it in regular yeast cells, so not spores. And the way it works in regular yeast is that if you give a small molecule called doxycycline, DOX, it should diffuse into the cell and then start turning on production of green fluorescent protein, which will make the cell green. So that's how it works in regular yeast cells, but we starved those to form spores out of it and try to do this experiment in the spores. And long story short, it turns out that you can force the spores to become green, so they without any nutrients. So these spores are just in water. Not only that, they make almost as high amounts of green protein as the ones, as the regular yeast cells that are feeding on external energy source, namely glucose. Okay. So gene expression, at least of GFP, is possible during dormancy, raising the question, why aren't they then apparently not doing anything at all? Now, since we're using a microscope to measure individual spore bags, we can actually quantify how green each spore bag is. And when you do that as a function of time after you force them, after you added doxycycline, so here I'm plotting the level of GFP on the y-axis. What you see are these individual gray traces, with each gray trace coming from a single spore bag. Now, there are two things to note here. One is that there's a huge variability in the amount of green proteins that the spore bags can make, even within the same population. So there's a huge spread in the grayness. The second thing to notice is that all of them eventually plateau. So the GFP levels plateau, meaning that these spores at some point, the amount of GFP doesn't go up anymore. And that's a little bit strange because this is something you see in regular replicating yeast cells. The GFP level in those cells will reach a steady state, but that happens because they're dividing, so they're diluting the internal GFP while they're producing it. So these two rates, the dilution rate of GFP and production rate, exactly match. But these are spores in water. They're not dividing, so they're not diluting away GFP, and yet the GFP level eventually stops. And with further work, we found that that happens because their production of GFP somehow stops, even though this doxycycline is always out there telling the spore to make more of it. And in fact, I won't have time to go into it, but this actually tells us that there's something fundamentally different about the way spores regulate their genes compared to regular yeast cells. But I will not go into it. But the most important point is that the hypothesis is in fact wrong. Because if you look in orange, these are the spores that are forced to make GFP, and the black are the ones that are not forced. And you see that there's no difference in the percentage of spores that can wake up after getting a certain amount of glucose. But as is the case in science, we got very lucky because we were wrong in just the right way that told us what to do next. So if you remember, spores have really different abilities to become green, right? So there's a huge spread in the gray traces here. So what Theo and I thought was that, or really what he thought was that, what happens if we just make a histogram of the different amounts of greenness in these spores in a population? So that's what this is. So here, what we're plotting, what we're asking is, okay, how many spore bags in a population can make, let's say, 2,900 units of GFP? So that's this bar over here. And now the question we ask is, now let's give these this population some relatively small amount of glucose. And then now we ask, if I look at only the spore bags that can make the same amount of GFP, namely, let's say 2,900 units, what percentage of those are able to wake up? And that's what we see here upstairs. And here there's a trend. It tells you that more green a spore can be, the more likely it's able to wake up. Okay, so the ability to produce GFP while you're dormant is somehow related to your ability to wake up after you get glucose. And that basically tells you that there might be some connection between the process of gene expression, namely how you get RNA from DNA and protein from RNA, and that turns out to be true. And we were able to manipulate these different processes to see how that affects germination. For interest of time, I'll just tell you something a little bit about this process, how you get RNA from DNA. And so to do that, you need this machine called RNA polymerase, and there are 3 different kinds. One of which, it's a bit of a wonky graph here, but basically what we are able to do is we are able to engineer the spores so that these RNA polymerase machineries are fluorescent. So they actually have, they give off red light, if you will. And just by looking at how red a spore is in dormancy, so each data point here comes from a single spore bag, we find that there is a positive correlation, namely that if you have more of RNA polymerase inside of you, then you are able to become more green when we force you to become green, okay? And so long story short, after these kinds of experiments, we find this kind of a triangular relationship where basically any pair of items that you can see here are highly positively correlated. So meaning if you have high ability to wake up after getting glucose, then you also have high ability to make a lot of GFP. And you also happen to have a lot of RNA polymerases. Now, there is a little bit of a subtlety here, which is that here we are forcing them to make GFP. Those ones tend to have a lot of RNA polymerases, but forcing them to do something doesn't actually tell you whether they are doing something when you don't force them to. And for interest of time, I won't go into it, but it turns out that they do. And in fact, they do express genes other than GFP, and those turn out to be very, very important. So really, I think this kind of a relationship, at least with the amount of time we have here, kind of tells you that there's something that you can look at which determines their ability to wake up. Namely, it's their ability to express genes while in dormancy that determines what chance they have of waking up. And just very quickly, I'll tell you why they age and die. So now we've determined that there's something happening in these spores, namely gene expression. And when you have a process that's happening over time, there's a potential to age because there's a flow of time, right? Something is happening. And indeed, okay, it's a bit complicated, but if you leave these spores in water without any sugar, and you ask what percentage of them are still alive, and you can check for that by giving them maximum amount of glucose and see how many of them can still wake up, you find that basically less and less are able to wake up over time. So there's death occurring over about 80 days if they are starved of nutrients. And during this time, if you now try to force them to make GFP, you see this blue curve here where they're less and less able to make GFP. And then the dead spores that you find in this population are not able to express GFP and in fact any genes, okay? And so long story short, we found out actually why they die. So as the spore, as days pass by and weeks pass by without any nutrients, important molecules that are stored inside of the spores that are important for gene expression are degrading away, they're being lost. It turns out that they're also being created, as I will quickly tell you, but there's a net loss of these molecules. As they lose these molecules, their ability to express a gene like GFP is going down. And even though I didn't really tell you, as that goes down, the amount of glucose that you need to give to them to guarantee with 100% certainty that they will wake up, that amount is increasing. And if you put these two things together, what you see is that as time passes by without nutrients, a spore needs more and more and more and more glucose. And in fact, eventually, it's more than you can ever physically give them. It's more than the saturating 2%. You will need an infinite amount. And that, by definition, means you're dead. So just as a proof, it turns out that as you age these spores in water without nutrients, indeed, molecules that are important for gene expression do decay away. So for instance, the RNA polymerase level does go down. And this actually happens, it turns out, because these molecules by thermodynamics, they do degrade very, very slowly, like 9 days. They also produce them, but incredibly slowly on a time scale of about 20 days. In a regular yeast cells, you should never see these in days. These are supposed to degrade or produce in minutes, not days. And we're investigating why that occurs. So, so there's a net loss, which is inevitable, and death is inevitable in these spores. So, okay, this is a complicated story, but I've just shown you what I just told you. So with that, I want to thank Theo for really doing all the work, and also for really coming up with basically all the ideas, the funding sources, and I want to thank the symposium organizers for giving me this opportunity and also organizing this. Thank you.
That was such a fascinating talk, Hyun. Thank you so much. The comment box is so full of awe and love for your talk.
Okay.
We don't have any questions from the audience, but I have. So you say that there's this three-way correlation between the gene expression that you bumped up, and the protein production, and the ability to make the spore bag. That's the one. Yeah. Are you able to sort of extrapolate that to other kinds of yeasts other than just baker's yeast? Is that something that you think might be ubiquitous among all kinds of yeasts beyond?
The short answer is I don't know. I think what's actually more well known about, so dormancy itself is very poorly understood, and almost everything we know about spores come from bacteria rather than fungal spores. There's a kind of fungal spore that is actually very, very interesting, maybe more interesting than baker's yeast, and those are the ones that cause infections. So for instance, I'm blanking on the name, but some spores are really deadly, and they're very difficult to kill. So it would be wonderful to extend maybe these ideas to very infectious spores that are difficult to kill because, well, we don't understand up to this point how they die. Yeah.
So we did have one question in the Q&A box, but it was the same question that I just asked. So hopefully, Kate, that's given you your
meningitis. That's the one. Yeah, the spores that cause meningitis. Yeah. So those are would be interesting to kill somehow.
Right. Mm. Thank you so much for your talk today. It was great by everyone everywhere. So let's have a round of applause for Hyun.
Thank you.
And we're going to welcome to the virtual room Shrouk El-Attar. Shrouk, are you there? Hello.
Hello, I'm here. Is this working?
This is working. We can hear you here.
Hey, how you doing?
So, doing well, thank you. You're about to give us a talk on how to be a kick-ass woman in STEM. Are you all ready?
Yes, I am. Let me try to share my screen.
Off you go.
I'll also share my sound. I love how normal this has become. Can you see my screen? Is this working?
Yeah.
Lovely, cool. So I'm actually going to start with a quick exercise. I will give you 10 seconds to grab a pen and paper, okay? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Do you have a pen and paper? Anybody on the panel? Feel free to unmute yourself.
I have one.
Yeah. Okay. So I want you to divide your paper into 4 sections like this. And then I'm going to need you to be super, super, super on it because you only have 10 seconds to complete each task. Are you ready? Matthew, you can say yes.
Yes, sorry, yes, I'm ready. And other panelists, please unmute yourselves.
I'm trying to find my pen.
You trying to find your pen? Okay, I'll give you 3 more seconds. 3.
Oh God.
2, 2.5.
Got it.
Got it? Yes. Okay, cool. All right. In the first box, I want you to draw me a nurse in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. No cheating. This is the end of the nurse. And then in 3 seconds, I want you to give this nurse a name. In 3, 2, 1. I can't wait to see those beautiful drawings. Okay. In the second box, I want you to draw me a firefighter in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay? In 3 seconds, give your firefighter a name. In 3, 2, 1. Are you ready for the next one? It gets harder.
Oh God.
Yeah. Okay. I want you to draw me a rocket scientist in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And give your rocket scientist a name in 3, 2, 1. You'll be glad to hear that the next one is the last one. I want you to draw me a engineer in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And give your engineer a name in 3 seconds. 3, 2, 1. Pens down! Pens down! No cheating, no cheating, no cheating. Okay, we're gonna park this on the side for a minute, but first I've got a question for you. How many triangles can you see in this picture? Just shout some numbers at me.
2.
2.
8.
Anybody else?
5.
5.
People
I'll wait for one more answer.
People in the chat box are saying 4, 8, 6, 5.
Okay, I actually see 2, but the answer is none. There are 0 triangles in this pictures. Our brains are amazing. They're constantly filling in the gaps for us so quickly that we don't normally have enough time to see what kind of judgment our brain came to fill in these gaps for us, what kind of unconscious bias we might have. So there are no triangles in this picture. And now I would like to introduce you to some of my friends. This is my friend John Cook, and he is a nurse. This is my friend Melissa Pinder, and she is a firefighter. This is my friend Bianca Kefalo, and she is a rocket scientist. And hello, lovely to meet you. I am Shrouk El-Attar, and I am an engineer. My name, Shrouk, means sunrise in Arabic. This is how you write it in Arabic. But if you want an easy way to remember it, you can just imagine a little shrew and put a K in the end. Shrouk. I go by both she or they pronouns. I usually say, you know, choose, but she is an engineer. It's such a powerful statement. And it shouldn't be, but we live in a world where it is. So actually, if you're talking to me about engineering, if you're talking about me as an engineer, I would prefer for you to use she pronouns. So I was named in the BBC 100 Most Influential Women in the World, United Nations Refugee Agency Young Woman of the Year, and Institution of Engineering and Technology Top 6 Young Women Engineers in the UK just last year. And this is my talk, Young People in Tech, a guide on how to kick ass. Okay, so there's something really strange going on in my talk, so I want you to pay attention, and then I'm going to test you in a little bit and see if you've noticed something, okay? So just have a look, notice what might be strange. So I was born and raised in Egypt, and I was first introduced to the term homosexuality when I was a little girl, and I just remember before that not knowing that it had a name. I just thought, okay, people are attracted to boys, but everybody's attracted to girls too, right? Right? No, can you hear like the beeping outside?
Yep.
Can you? Oh my God, I'm so sorry about this. Is it too loud?
No, you're okay. This kind of
Okay.
thing happens.
Okay, so, oh, it's over. Thank you, car person. I'm really glad you have stopped the beeping. Where were we? There we go. One of my earliest memories was realizing that people on my TV screen are not actually tiny little people living inside it. And for me, that was just a form of magic. I was like, how do people make this? I didn't realize that it was called electronic engineering. I just thought it was some sort of sorcery. So I got obsessed with electronics, and I used to take everything apart, including my mum's mobile phone, which didn't make her very happy. My mum looks nothing like that, by the way. So I studied really hard, and I was supposed to be one of the youngest to study engineering at university. I skipped 2 years, and I was super excited to finally study this magic. Anything strange? Has anybody noticed anything strange about the slides so far?
I think I have.
Yeah?
All of the cartoon pictures you've got are white people.
Yes, they are. I've been given a version of this talk for about 6 years now, and there's been so many times where there's been even brown and black people in the audience who wouldn't have noticed that. And I myself, so I love using cartoons. I think they make my talks really fun. And for the first couple of years, I didn't realize that I used people who looked nothing like me, because whiteness is such the default. You just take it at face value, it just becomes normal. So I just wanted to show you like what comes up when I kind of look up geek cartoon, and it's all guys. And then geek cartoon girl, but then they're all still white. And then geek cartoon girl brown. Brown seems to just mean your hair color. Geek cartoon girl black, finally we get somewhere, but some of them are a bit hypersexualized, and there isn't really as much choice. I encourage you to go and try this yourself with anything really. But thank you for noticing. I'm glad you noticed. So in 2007, I came to the UK. Can you guess which person I am? I'm going to give you 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Anybody? I'll move my mouse and then you can tell me if I'm in this row. Am I in this row? Okay, this row? This row? This one? Okay.
So nobody in the chat box has said anything, but I think you're second row back on the far left.
Second row back. This person?
The one below.
Ah, this person.
Yes.
No, I'm this person, but yeah, good guess. So when I was in year 3 or 4, I was taken to the principal's office for having natural hair because it was too messy. So I started straightening my hair every day, and it took me a really long time to be able to leave my hair as it is and accept it normally. Yeah, I didn't straighten it because I wanted to. I straightened it because I felt I had to. So anyway, I went to KICKASS High School and I did my A-levels, and then I was super excited to finally study this magic at university. So I applied to universities and then found out that I couldn't access university, not because I was incapable, but because I was an asylum seeker. I also wasn't allowed to work. I wasn't allowed to travel, so I couldn't leave the UK and trying to get an education somewhere else. I was trapped for many years. That's why when I found out that I could be a STEM ambassador without being an engineer, I jumped at the opportunity. I was like, hey kids, like I'm not allowed to study engineering, but let me teach you about it anyway. I taught kids how to do things like build hydroelectric generators from trash. In 2012, I was asleep at a friend's house and there was a dawn raid on my family home. They broke into my family home. Immigration officers in the riot gear dragged my little brother and sister out of bed and my mum and deported them to a country I'm not allowed to visit. I was left behind. I was the only person who was left behind. And not much longer later, some months later, I was given the right to stay in the UK. There are no amounts of words to describe the grief that I was in for losing my family so suddenly, but I wasn't going to let this go to waste. And the first thing I did when I got refugee status, when I was allowed to stay in the country indefinitely, was apply to study engineering at university. And over there, I continued my STEM work, and I've been a STEM ambassador for 9 years now. Makes me feel a bit old. I've done a lot of cool engineering projects. I worked with surgeons operating on the eye. I built a system that helps with eye surgery. I then did my year in industry at Intel. I co-founded Intel Inspire, which is a STEM outreach group over there. And then I came back after my year in industry and I built a car and raced it. I then went to Japan and I worked on optical network communications for Fujitsu. And I presented about my role in Japanese. I was actually offered a permanent role after that, but I decided to come back to the UK to do my master's in electron spin resonance. Has anybody heard of electron spin resonance before?
I
No?
have,
Yay!
I think.
Would you feel comfortable to describe what it is?
Probably not, no.
No problem, that's okay. So if you've not heard of ESR before, electron spin resonance before, it's similar to NMR, but if you've not heard of NMR, it's a little bit similar to MRI, and everybody's heard of MRI before, I think. I'm
Yep.
gonna say yes.
Yeah. I've heard of NMR.
You've never heard of NMR?
I've heard of NMR as well.
Okay, well, it's a lot closer to NMR, but I'm just going to describe MRI because most people are familiar with MRI. So MRI, you're resonating the water molecules themselves, but with electron spin resonance, you're actually exciting the electrons themselves, and you're exploiting their electron quantum spins. So they've got a spin of +½ or a -½ and that difference between both is something we call the Zeeman effect. But let's not go too much about this. This is what an ESR machine actually looks like. It was built in the 1940s. As you can see, it's huge. It fills a whole room. How much do you think it costs? Shout
Cool.
Far
numbers.
too much.
Far too much. It goes, you know, from hundreds of thousands of pounds up to millions of pounds. So for my master's, my aim was to create something that's cheap, portable, and modular, but does the same thing. And I created a successful ESR signal in an area that's less than 1 meter square. And instead of costing hundreds of thousands of pounds, only cost me £300 to make. Imagine a future where people can check for things like cancer from something as small as their mobile phone. I'm just super excited that my research has gone towards that future. And then I joined Venetia for a couple of years I built robots for a living. And some of the robots that I built can measure things up to a single nanometer, which is 60,000 times smaller than a single hair. Met with the company CEO a few times, and over there I've co-founded the company's first diversity and inclusion network. And now I work for a really cool company called Elvie. Has anybody heard of Elvie before? No?
Only after our chat, but, but people in the chat box are saying yes, they have.
Oh, some people have. Thank you for reading the chat box for me. So I make technologies for cisgender women or transgender men or some non-binary people, basically anybody who can breastfeed or give birth or has vagina. So some of the things I make are silent breast pumps or pelvic floor trainers. If I talk about the silent breast pumps for a minute, like they're breast pumps that go in your bra and you can just kind of go about your day and do normal human stuff. But before that, it took 160 years to come up with a design that's not literally a copy paste of what we have for cattle. It took 160 years to realize that people who breastfeed are actually not cattle. They're actually not animals. Well, we're animals scientifically. And for Kegel trainers, so pelvic floor trainers, so people who've given birth, about 80% of them suffer incontinence. So they lose control over the bladder. Even though it's a huge percentage of people that suffer this, most people have never heard of it, or most people don't know that that's a problem, or a lot of people who actually do get pregnant don't know that that's going to become a problem until they actually become pregnant. And it's just so upsetting that it's such a taboo that we don't even talk about it, because they are issues that we say are women's problems or whatever. So I do love transform people's lives for a living. I really love what I do. I really love my job. Being an engineer is my superpower, but I wasn't always allowed access to engineering, like I said before. So I joined Student Action for Refugees, and I campaigned for equal access to higher education for asylum seekers. I addressed the British Parliament a number of times. I spoke to tons of vice chancellors, and today I'm super excited to say that the Equal Access campaign is successful at more than 75 universities across the country. So more than 75 universities now allow asylum seekers to study. There is probably, I think, about 108 universities in the whole country. I think that it's a dream that can come true, to make the whole country a nation of equal access. Anyway, I'm an engineer by day, belly dancer by night. I have built a machine that can detect cancer, and I've also belly danced around the world, countries as far as India, countries as far as Japan. But growing up, I was told I have to choose between art and engineering. And to these people, I say, embrace the power of and. You can't just do both. You can do both and kick ass at both. So I mixed two of the biggest parts of my identity, being queer and being Egyptian, the queerest of art, drag, and I mix it with the most Egyptian art, belly dance, to make dancing queer. I would like to show you a video of me dancing, if that's okay. those days where you could dance with like crowds and stuff. So I donate 50% of everything I make as dancing queer, or if I'm giving a talk or a workshop, to LGBT plus initiatives in Egypt. So if you've booked me to do any of these things, thank you, because you have funded people to go to safer housing or be released from prison after being in prison just for falling in love with somebody of the wrong gender. So thank you for booking me. So before I finish, I want to say something that's really important for me, but also something that I've been finding really hard to talk about until really recently, about 6 months ago, probably. So the truth is, I almost quit engineering entirely. I worked for a manager who made me feel like I was an awful engineer, like whatever I could do, I'd never be good enough, and really just broke my confidence. And you know, I don't think that quitting is for losers or anything like that. I think knowing when to quit is such an important quality, such an important skill, but that time was not it for me. And had I quit then, I would have not been able to talk about almost any of the things that I talked with you about today. So from this, I've learnt 3 things, and it's to take up space, make sure that my voice is heard, and I will not apologize for my hair. I will not apologize for the way I look. I will not apologize for being queer. I will not apologize for being a woman. Be unapologetically your authentic, true self. Thank you for coming to my talk. These are all the social medias you can stalk me on. Please stalk me. I also recommend you watch BBC's documentary, No More Boys and Girls. And I'm reading this book called Invisible Woman right now, and I'm so angry at everything. I recommend that as well. Thank you for having me. I'd be happy to take some questions now if you like.
Shrouk, thank you so much. Before we move on to the first question, I just want to show you what I drew.
Oh my God, I want to see it.
So we've got on the top left the nurse Jerry, who is a stick figure wearing some scrubs. Top
Love
right,
it.
we've got a firefighter with pants and braces called Luke.
How
Bottom
did you
left,
do that in 10 seconds?
I'm quick. That's what all the boys say. Bottom left, we've got Deborah, the rocket scientist, a flask. And bottom right, Amanda is the engineer who's got a spanner.
Yes, I love this so much. I love it so much. Does anybody else want to share with me theirs?
Tell you what, if you want to share your drawing, tweet it, take a photo of it and tweet it with the hashtag SVVS20. That's STEM Village Virtual Symposium 20. And we'll go check them out as well. Shrouk, while we're getting to questions, would you mind putting some of your contact details here into the chat box so people can copy and paste them or follow through?
Yeah, of course. Yeah, that makes sense.
And I'm not seeing any questions coming up, but I'm going to ask one myself.
Okay.
Between audacious engineering goals of having a pocket-sized cancer detector, petitioning, speaking at the several times, and just dancing in front of crowds of strangers. It's very obvious that you've got big ambitions and the confidence and drive to go and achieve those goals.
Or ADHD.
Or ADHD. What's your advice to somebody who has a goal but thinks it's beyond them?
Who has a goal, who thinks that, honestly, about like, even if you just told me like 4 or 5 years ago that I'd have an award from like the United Nations or the Institution of Engineering and Technology or the BBC, like I would have never believed them, because I thought they were unachievable. I've not seen people like me represented in these awards. Like growing up, I thought I had to be my own role model, and I shouldn't have grown up in a world where I felt like I had to be my own role model. But I really think, you know, if you can't see yourself represented, be your own role model, go for it, do it. If you think it's beyond your reach, it's not true.
Absolutely. To that end, Kate Oliver asked, what can we do, people here at the conference, do to support you, your causes and your people?
Join the Equal Access campaign, please, especially if you're at university, if you're an academic, or if you're a student. join Student Action for Refugees. Most universities would have a society. If there isn't a society called Student Action for Refugees, get in touch with me and I'll help you set you one up. But yes, find out if your university has equal access for asylum seekers. And if not, maybe you can help me or help everybody else make that a reality. If they do have equal access, I think it's so important to thank people, because I've done so much activism and it's tiring when all you get in return is criticism. So if your university has adopted equal access, make sure you tell them that this is something you appreciate.
And have you got a link or a website for Equal Access campaign that people can go and look at?
If you look up Student Action for Refugees Equal Access, it will be the first thing that turns up.
Fantastic. Thank you so much.
All right. Thank you.
We've got one more question from Giles Oldroyd. Yeah, they're coming in thick and fast now.
Oh, look at that. I don't know where to put the chat box, but it's okay. I'll just do it after.
So Giles asked that you mentioned in there was a low moment where you thought about quitting engineering. What was it that persuaded you to stay?
I think while at work, I wasn't surrounded by necessarily supportive people in that specific scenario. At home and outside work, I had some really good mentors. I actually had so in the same company, I had a manager who noticed that I was behaving differently. So I'm a really social person. I started eating lunch at my desk, and I started not really talking to anybody, and I didn't say anything. But then my previous manager was like, "Hey Shrouk, like, are you okay?" And I was like, "Oh, I think I'm an awful engineer, help." And he was like, "No, I worked for this guy before, like, he's just a bully." And that's when I stopped blaming myself, and having somebody else who worked with me in the same capacity, who believed in me, who told me, "Shrouk, you're one of the most brilliant engineers I've worked with," was really what helped. And I don't know, you need to surround yourself by supportive people. And if that's not there, I think it just makes it so much more difficult. I was lucky, I guess.
Right. It is so important to make sure, you're being uplifted in everything you do, and somebody who's going to bully you is not someone whose words you need to take with weight.
Totally.
So thank you, Shrouk, for this talk. If there are more questions, or if you want to see more of Shrouk, you are after the short break that's coming up just now, we are going to be having a drag panel. We'll start with some words from Sue Dukas, and then we're going to have the Shrouk El-Attar, Dancing Queer, Sassy Science, Diva Attenborough, and a queen whose name I've forgotten because I'm a bad chair. But
I think I remember her name, Diva Attenborough and Yoroku. No, it's okay. Sorry.
Yeah, we'll get there. I'll have a name for after the break. I'm so sorry. If Hyun Youk, if you can pop your contact details as well. Hyun Youk was our first speaker for this session. Pop your contact details into the chat in case somebody wants to get in touch with you. That would be fantastic. And we'll be back in about 15 minutes with 10 minutes with some words from Sue Dukas. So stay right there.